Dropout is another regularization technique which may help to prevent overfitting. The term dropout refers to randomly dropping out neurons either in the input layer or in the hidden layers of a neural network. This corresponds to temporarily removing some neurons from the network along with all its in and out connections. Dropout can be seen as extra layers applied after regular layers, whose aim is to zero the output connections of some neurons in the previous layer. This is done by sampling independent Bernoulli masks depending on the parameter p, the dropout probability. This parameter p is the probability of zeroing a neuron in a dropout layer. This is the only parameter of a dropout layer which is set to 0.5 by default. You can also apply dropout to the input layer, but in this case the dropout probability is generally set to 0.2 in order to keep more neurons on average than in a hidden layer. Beware, in the original paper describing dropout, the authors mentioned p as the probability of retaining a neuron. However, in most implementations, the dropout parameter p corresponds to the probability of removing a neuron. Finally, you can apply several layers of dropout in a network. For each of them, you can choose a different dropout probability. Keep in mind that all neurons are removed independently from each other, whether they are in the same or in different layers, because the sampled Bernoulli are independent. Here is an illustration of dropout. Consider the network on the top left corner. Applying dropout in this network amounts to removing some neurons randomly at each optimization step. In one such step, the neurons are removed and the corresponding network is depicted on the bottom left corner. The input and output connections of each corresponding neurons are removed. Thanks to this procedure, different sets of neurons activate at each step, which introduces noise and diversity into the training procedure. In particular, it prevents the network to use a specific neuron to recognize one specific observation, therefore preventing overfitting. At training time, a neuron is present with probability 1 minus p. As usual, the training procedure is dedicated to finding efficient weights and biases for all neurons in the network. These parameters are then multiplied by 1 minus p to obtain the final weights of the network. This is done to preserve the strength of each neuron in the prediction process, since a neuron at training time is present only with probability 1 minus p, whereas it is always present at test time. Indeed, the final network contains all neurons. There is no dropout at test time. Now let us describe the exact dropout procedure. Inside a given epoch, for each mini-batch of size m, the dropout procedure samples m different masks. A mask consists in a vector of zeros and ones of size equal to the number of neurons that we may want to remove in the network. Each component of this vector results from the sampling of an independent Bernoulli. The probability of removing a neuron in a network is typically of 0.5 for invisible units and 0.2 for neurons in the input layer. The output units are not removed. In the classic dropout procedure, one mask is drawn per observation in the mini-batch. Then, each observation is propagated through the corresponding network, the network in which neurons have been removed according to the mask associated with the corresponding observation. Each observation produces a loss on which a gradient can be computed via backpropagation through the mask network. Then the gradients are averaged across the mini-batch to form the final gradient used in the gradient descent procedure. At test time, the weights of a given neuron are multiplied by 1 minus p, where p is the probability of removing this specific neuron during the training phase. One common paradigm in machine learning is to try to average predictors in order to build more robust, more consistent, more performant predictors. So we could try to aggregate neural networks. Several ways exist to achieve this goal. The first one would be to randomize the dataset on which we train each network, for example via subsampling the original dataset, and then training each network on a particular subsample of the data. You have two problems with this approach. First, you may not have enough data to obtain good performances, but more importantly, this requires to train many networks, while the training of one specific network can already be very time-consuming. Secondly, the prediction, computed by averaging the prediction of all networks, would take more time than a prediction computed with a single neural network. The second way would be to create different networks and to train them on the whole training set. In this way, you do not decrease the size of the dataset at your disposal to train each network. However, the problems listed above are the same. It may be too computationally costly to train a large number of neural networks, and the prediction may take too much time. So it is quite complicated to aggregate neural networks. Fortunately, Dropout can be seen as an averaging method. To see that, imagine that you fix a network and you list all possible networks corresponding to all masked versions of the original one. For each network, you have a finite number of neurons, so you also have a finite number of masked versions, but of course this number is very large since it is exponential in the number of neurons. Now, imagine that these networks share their parameters. There is only one set of parameters for all these networks. Now, dropout corresponds to the fact that when you see an observation in a mini-batch, you sample a mask which corresponds to one masked network of the list. Then you put the observation in this masked network, backpropagate the loss, and obtain a gradient. The gradient are average over the mini-batch, that is, the gradients of m masked network are average, and this average gradient is used to update the weights. Since the weights are shared by all masked networks, they are all updated in the same manner at once. This procedure is repeated until convergence, and the final prediction results from the averaging of the predictions produced by all these networks. In this sense, you can see Dropout as an efficient procedure that allows you to compute the average of the predictions of all possible masked networks. This is particularly interesting since, as noticed before, a naive approach that tried to average predictors would be infeasible in practice. Seeing Dropout as an averaging method may help to understand its good performances.